Hello, in this lecture we are going to be discussing pumping lemma for regular languages. Now, pumping lemma is used to prove that a language is not regular. It cannot be used to prove that a language is regular. Now, what that means is that if we have a language A and we apply pumping lemma to it, if pumping lemma fails, then we are certain that the language is not regular. However, if it passes the pumping lemma test, then it could be regular or it could be not regular. We cannot be certain that it is regular. Now, moving on to the conditions of pumping lemma. Assume that we have a language A that is a regular language. Then A will have a pumping length P such that any string S where the length of S is greater than or equal to the pumping length may be divided into three parts: S equals X, Y, and Z, such that the following conditions must be true. Now, what this condition here means is that the pumping length which we are going to select, which has to be greater than 0, the length of the string that we are going to select has to be greater than or equal to the pumping length. Only then we can divide a string S into three parts, X, Y, and Z, and that string must satisfy these three conditions. Now, what these three conditions are: the first one is that we have our string X, Y, Z divided into three parts. Now, for the Y part, we are going to put powers of I on Y, and as we increase the power from 0 to any value, the whole string, the resulting string, must also be part of our language A. Now, our second condition is that the length of Y must be greater than 0. What that means is that the Y, when we're going to be dividing our string into X, Y, and Z, we need to select at least one character for Y. Our Y cannot be an empty string, it needs to have at least one character. And the last condition is the combined length of X and Y must be less than or equal to our pumping length. Only then it will be considered a regular language. So these were the three conditions. Now moving on to the steps that we use when solving a question involving pumping lemma. So in pumping lemma, we use the concept of contradiction. What that means is that first we initially assume that our language A is irregular. It is regular, and through a series of tests, we contradict our own self, and then finally we prove that in fact A is non-regular if it fails the pumping lemma test. Now, following the methodology, after assuming that our language is regular, then we say that it has to have a pumping length, say P. Now, P, as I said, we could select any arbitrary value which has to be greater than 0. It cannot be equal to 0, it has to be greater than 0. And then after that, we select our string S, and all string, we can select all those strings that are longer than P, and then those can be pumped. What this is the same condition that we discussed over here, that the string that we are going to select now from our language, it has to be greater than or equal to our pumping length. Find a string S in A such that the length is greater than the pumping length. Then we are going to divide our S into three parts, X, Y, and Z. And then we're going to show that as we increase the powers of Y, the resulting string does not belong to our regular language A for some value of I. And this is going to be our proof by contradiction that our language is not regular. Now, we will consider all ways that S can be divided into X, Y, and Z, which you're going to see in the coming example as well. and the resulting cases that we are going to have by dividing S in all the ways, then we're going to show that none of these, which we will select here, the cases, none of these can satisfy all the three conditions at the same time. Like there would be at least one that would be contradicting, and then we could say that S cannot be pumped. So this proved by contradiction that it is not regular. Now moving on to our example. So we have considered a language A, that is a to the power n, b to the power n, where n is greater than 0. Now we know this language is not regular, but how are we going to prove it through pumping lemma? The first rule that we have was to assume that A is regular. So we assume that our language A here is regular and is a pumping length B, which was here, needs to have a pumping length P. Now P could be any value greater than 0. I have selected P equals to 7 over here. Now, since it was A to the power n, B to the power n, and we needed to select a string S such that the length of string had to be greater than equal to our pumping length. So I considered the powers n to be equal to the pumping length. So we get a string that is longer than the pumping length. Here we have a string of length 14 while our pumping length is 7. Now you could have taken any power of n over here as long as the length of your string was greater than or equal to the pumping length. You should be fine. But to be safe, I took the power 7, the pumping length as the power. Now the next step that we had was to divide S into three parts, X, Y, and Z. And like I said, we will consider all the ways that S can be divided into X, Y, and Z. So these, in this scenario, we could have three cases of dividing our language into X, Y, and Z. The first one would be that our Y is in the A part. The A part was this A to the power n. So case 2 would be Y being in the B part, B to the power n. And the last part would be, it would be in between, is in between the A and B part. Well, it's overlapping the A and B part. So these were our three cases. Now we are going to be we're going to be applying this condition that as we increase the powers of I, the resulting string for some value of I uh, will not be part of our language A. Now here, as you can see, as I apply the power 2 to Y, we get 11 A's. Now how do we get them? This is, we had 4 A's here, we applied power 2, we got 8 A's in the Y part, and yeah, we got 8 A's in the Y part, and total we got 11 A's and 7 B's. Now our language is A to the power n, B to the power n, so we need to have equal number of A's and B's. So this resulting string is not part of this language A, so it fails the condition. This first condition, our first string has failed. So now checking for case number 2, where Y was in the B part. Again, it's the same thing. When we apply Y to the power 2 on the B side, we could see that again the number of A's do not equal the number of B's. So this case also fails the first condition. And finally, looking at our last case where it was overlapping the A part and the B part. Now, as you can see, although we have equal number of A's and B's in the case 3, but the issue that we have is that after we are having A's after B's right here, which should not be possible in our language A, because first we're going to have all the A's and then we're going to have all the B's. But over here we can see that we have A's, then B's, and then again A's, which is not part of our language A. So the third part also fails the first condition. Now, as we said that show that none of these can satisfy all the three pumping conditions at the same time. So we have proven here that all three cases cannot satisfy at least one of these conditions. So we could say here by contradiction that although we assumed our language was regular at start, but it breaks the pumping equality. That is, it's not part of our language A to the power n, B to the power n, the resulting strings. Therefore, the language A is not regular. Now, this was a basic example, and they all three failed for the first example. How uh, for the first condition. However, we could also see that some of these might even fail the third condition. So now let's look at the third condition, which is uh, that the length of x, y combined should be less than or equal to our pumping length, which was 7. Now, if we see in the case 1, the length of x and y combined is 1, 2, 3, 4, 5, 6. 6 is less than or equal to our pumping length 7. So case 1 satisfies the second condition. For case 2, if we count the number of x and y's, 3, 4, 5, 6, 7, 8, 9, 9 is length of x and 4 is length of y, that is 13. 13 is not less than or equal to our pumping length, which is 7. So case 2 even fails the third condition. So yeah, well, we could look at all the conditions as well, but since each case has failed at least one condition, we can conclude, as we concluded, that language A is not regular.